Electronics. This is a mock test of electromagnetic theory. In this video, I've tried to include maximum numerical and difficult questions because for GATE exams and ISRO exams, maximum numerical questions and difficult questions can come. So in this video, you can face a lot of numerical questions. And if you found the video useful, please don't forget to like, share and subscribe. Next, you can see the questions, and also if you want, you can download the notes of this video in the description. Okay, so let's see the 10 questions. Now we are going to see the solutions of 10 questions which you have already seen. This is EMT mock test video. The first question is, for static electric field and magnetic fields in an inhomogeneous source free medium, which of the following represents the correct form of two of Maxwell's equations? So we have recently done a video on Maxwell's equations, and it's a quick revision how to remember the 4 equations of Maxwell. All those things we have done a video. So this question is connecting to the static nature of electric and magnetic field and how the Maxwell's equation is getting modified according to the equation. Okay, so first let us see the Maxwell's equation one by one. The first equation is del dot D equal to rho V, or you can write it as del dot E equal to rho V by epsilon, or rho by epsilon. Okay, second equation will be del dot B equal to 0. Third equation is del cross E equal to minus dou B by dou T. Okay, I'll write it as rho itself. Okay, del dot D equal to rho V. Then the last equation, or the fourth equation, is del cross H equal to J plus dou D by dou T. So these are the 4 equations of Maxwell. We have discussed about in detail in the video of Maxwell's equation revision. Okay, now we are going to talk about the static electric and magnetic field and how the equation is getting modified. Okay, so when static electric field and magnetic field is considered, the equations will be del dot D equal to rho V. You can also represent in terms of E. Okay, del dot E equal to rho by epsilon. Likewise also you can write. Then this will be del dot B equal to 0 itself. I hope you can see it. So this is del dot B equal to 0, and this will be del cross E equal to, here we are going to consider the static magnetic field. So dou B by dou T is equal to 0. Okay, there is no change in the magnetic field, so it is 0. So this is a change. Then next one is del cross H is equal to, there is no varying electric field. So this current term will get cancelled. So it will be only J. Okay. So in order to have more clarity about these 4 equations, please do watch the video on Maxwell's equation. Okay. So this is actually 2 currents. This is the normal electric current, and this is the displacement current density. Okay. So here the displacement current due to the varying electric field will actually get changed because there is no change in electric field. It is static. Okay, so this will be the new equation set. Okay, so the option correct here is, the 4 options are given. From the 4 options, these 2 equations are given in option D, and that will be your correct answer. It is del cross E equal to 0 and del dot B equal to 0. I'll read it once again. Del cross E will be now 0. Why? Because there is no varying magnetic field. So that term will get 0. Dou B is actually evaluating the change. There is no change, so it will be 0. Then del dot B equal to 0. It is same in the previous case also. So this will be your equation, and the correct answer is option D. I hope it is clear. Okay, so in this equation we are discussing about the static electric and magnetic field and how the Maxwell's equation is getting modified. Okay, correct answer is option D. Now moving on to the second question. So these equations, its relations and all very important in EMT subject, especially for GATE and AFCAT exams. Moving on to the second question. You can see the question on board. If the flux density D equal to 5ax minus 4y, 5x ax minus 4y ay plus kz az microcoulomb per meter square, and the magnetic flux density B equal to 2ay, find the value of K to satisfy Maxwell's equation if sigma equal to 0 and rho V equal to 0. Okay, so what all things are given here? The value of the flux density is given 5x ax. I will write it below. Okay, so D flux density is given 5x ax minus 4y ay plus kz az. Okay, so this is your flux density. Now other terms are given. Sigma is equal to 0 and also rho V volume charge density is equal to 0. Okay. Now if you have these two equations, that is you have the equation for flux density and you have this relation also. Now you can substitute in the Maxwell's equation. Here again Maxwell's equation is coming into play. There is a Maxwell's equation. Just now we have discussed del dot D equal to rho V, right? So here it is given that del dot D equal to rho V, and also in the question it is given rho V is equal to 0. So you can equate rho V as 0. So we'll put del dot D equal to 0. Now we have D. See here D is given to you. Now take the divergence of it. Del dot D. Take the del dot of this vector. That is dou. This is Ax term. So dou Ax by dx, dou x by plus dou Ay by dou y plus dou Az by dou Z. Likewise, take the divergence and equate that to 0. You will be getting the value of this K. So I am going to do this. So I am going to take the del dot of this D vector. So del dot D, I am going to evaluate dou dx by dou x plus, since it is D vector, we are taking dx, okay, plus dou dy by dou y plus dou dz by dou z equal to 0. Now substitute these coefficients in dx, dy and dz. You will be getting, this is 5x, here 5x, here it is minus 4y, and here it is kz, right? So that are the coefficients. So if I equate, take the dou by dou x, dou y, dou z and equate the resultant to 0. So if you take dou 5x by dou x, you will be getting 5. Okay, I'm going to write the value above. So 5, if you take this term, if you evaluate this term, you will be getting 5. If you evaluate this term, there is a minus. Don't forget to take the minus. It is minus 4. Okay, minus 4 you take outside. Dou y by dou y get cancelled. So it is minus 4. Then here if you evaluate, you will be getting k. So plus k equal to 0. That is your result coming. So if you calculate this, 1 plus k equal to 0 or k equal to minus 1. So the correct option here is option B, which is minus 1 is your correct option for your second question. I hope it is clear. So in this question, you have been given the D, that is the flux density. And also, you have been given the magnetic flux density, but you don't have anything to do with that term here. Now, you need to find only the value of K. And also it is given sigma equal to 0 and rho V equal to 0. You just need rho V equal to 0, that term. And by applying in the Maxwell's equation, you have del dot D equal to rho V. So you can substitute rho V as 0 and then take the del dot D, and by evaluating, you will be getting K equal to minus 1, which is option B is your correct answer for your second question. Moving on to the third question. So I've tried to include a little bit difficult questions in this video. Third question. A lossy material has mu equal to 5 mu 0, epsilon equal to 2 epsilon 0. The phase constant is 10 radians per meter at 5 megahertz. The loss tangent is dash. Okay, you need to find what is the loss tangent. Now, what is the expression for loss tangent? You call loss tangent by variable x. You can denote using x. That is sigma by omega. Epsilon is your loss tangent. Okay. So, you need to find what is loss tangent, which is sigma by omega epsilon. Now, here in this question, what all details are given to you? You have been given what is mu. I'll write it here. Mu equal to 5 mu 0. Epsilon is equal to 2 epsilon 0. And the phase constant is given, which is represented using beta equal to 10 radian per meter. And frequency is given 5 megahertz. So, 5 into 10 raised to 6 hertz. So, these are the details given to you. Now, how to find the value for the loss tangent from these variables or these given data? We will write the equation for beta. Beta is equal to, the equation is omega into square root of mu epsilon by 2 into 1 square root of, inside also there is a square root of 1 plus sigma by omega epsilon square plus 1. So this plus 1 is, so this is the equation for phase constant beta, and I'm going to substitute the values of the given variables into this equation. Also, I know the value for my phase constant beta. Okay, so beta is 10 equal to omega. You can write it as 2 into pi into f. F is given here 5 into 10 raised to 6 megahertz. Sorry, 5 megahertz. So 5 into 10 raised to 6. Now, inside the bracket, there is mu epsilon. What is mu? Mu is 5 mu 0. Epsilon is 2 epsilon 0 by 2. Right. Now, there is a square root of mu 0 epsilon 0 here. So, you can take, okay, you can take it outside. But after substituting the other terms, we'll take it outside. Into square root of 1 plus x square plus 1. So, this plus 1 is outside this square root. Okay. So, this is your expression. Now, I'm going to take this mu 0 epsilon 0, which is a square root. It is square root of mu 0 epsilon 0 outside this, and I'm going to write that in terms of c, because you know square root of mu 0 epsilon 0 is equal to 1 by c. So, we can remove this, and I'm going to write it as separate. I'm not taking it outside the square root. That is, along with this square root, mu 0 epsilon 0 is 1 by c. So, you can remove it and write it as 1 by c here. So, c is 3 into 10 raised to 8. Okay. So, this is a 1 by c. Just remember, square root of mu 0 epsilon 0 is equal to 1 by c. So, that's what I have substituted here is 3 into 10 raised to 8. So, now there is only 5 into 2. Right. Remaining all terms is, that is x we need to find. All the other values we have substituted. Okay. Now, if you solve it, you will be getting the value for x, that is equal to sigma by omega epsilon, which is 1823 is the value which you are getting. So, what we have done here is we have written the equation for your phase constant beta. Phase constant value is given 10 radians per second. So, we have first written the equation for the phase constant. We have substituted sigma by omega epsilon as x here. So, this term was actually sigma by omega epsilon square, which we have taken as x. So, we have replaced it with x square. And remaining other variables are given in the question directly. So, we have substituted it as it is. Also, we have taken this substitution. Square root of mu 0 epsilon 0, which was here. We have taken it 1 by c and we have written it here. Okay. So, other terms are as it is. And we have found the value for x, which was sigma by omega epsilon, and we have obtained the value as 1823. Okay, so the correct answer here is option B. So this is a little bit difficult question actually. For GATE exams, you can expect these type of questions. Okay, so anyway, I hope you understood the question. The question was to find the lowest tangent. Okay, so by using the phase constant equation, you can find the lowest tangent. Anyway, the correct answer here is option B. Moving on to the next question. Next question is question number 4. Fourth question is, a wave propagating in a lossless dielectric has components E equal to 500. I'll write the components. So we have E equal to 500 cos 10 raised to 7 t minus beta z AFCAT volt per meter, and H magnetic field component 1.1 cos 10 raised to 7 t minus beta z AY cap ampere per meter. So these are the two field components, electric and magnetic field components given to you. If the wave is traveling at Vp 0.5 c, phase velocity Vp is equal to 0.5 c, and c equal to 3 into 10 raised to 8 meter per second, then mu r epsilon r values we need to find. Okay, so that's the question. So how to find the value of relative permeability and relative permittivity? That is a question. Now we can use the relation for intrinsic impedance here. We know that intrinsic impedance eta is equal to Ex by Hy. That can also be written as square root of mu by epsilon. Right. So we have here, this is the wave traveling or the electric field component in the x direction. So here Ex is nothing but 500. Also magnetic field component is in y direction. So this is Hy. So Ex by Hy is equal to 100 by 101, right? So I'm going to remove this and I'm going to write it as not 100, 500. 500 by 1.1. So this is the value for Ex by Hy, which is equal to eta, which is the intrinsic impedance. And that is equal to mu by epsilon. Now how can you write mu? Mu you can write as mu 0 mu r by epsilon you can write as epsilon 0 epsilon r. Also you can take this mu 0 epsilon 0 square root as separate and you can write it as 120 pi. That is a constant value. Everyone should be knowing that. When studying EMT, that value should be known as by heart. So mu 0 by epsilon 0 into square root of mu r by epsilon r. This you can replace by 120 pi. Okay, so this is the first relation which we have, that is 500 by 1.1 equal to 120 pi into square root of mu r by epsilon r. Now this is the first relation which we have. The second relation is taken from Vp equal to 0.5 c. Okay, so please note this first relation. I'm going to remove it. Okay, this will keep it. The second relation, it is given that Vp equal to 0.5 c. Okay, and also the value of c is given to you as 3 into 10 raised to 8 meter per second, but we don't need the value for c here. Now Vp, we know that Vp can be written as c by square root of mu r epsilon r, and this is equal to 0.5 c. So this c and c is getting cancelled, and this is our second relation. Okay, now we have two relations, and the unknown terms are mu r and epsilon r here, and also here mu r by epsilon r. Now if you solve these two equations, so this is your first equation, and remove this part. Okay, so this is your first equation and this is your second equation. Just try to solve these two equations. The value for mu r and epsilon r obtaining is mu r equal to 2.42 and epsilon r equal to 1.65 is the value getting. 2.42 and 1.65, and the correct answer is option B. Okay, So here we have taken directly the equation for intrinsic impedance and we have substituted the value for phase velocity Vp. C by square root of mu r epsilon r. And we have equated the two equations, and that is, one is this relation and this relation we have equated, and we obtained the value as 2.42 and epsilon r equal to 1.65. Correct answer is option B. Now, moving on to the fifth question. Fifth question is from transmission lines. A transmission line has a characteristic impedance of 50 ohm and a resistance of 0.1 ohm per meter. If the line is distortionless, the attenuation constant in Newton per meter is dash. So, here the question is regarding a transmission line, and it is a distortionless transmission line. And for the distortionless transmission line, the relation is like this: L by C equal to R by G. So we all know that transmission line can be expressed or represented in terms of the basic components like resistance, inductance, capacitance, and conductance. And when the line is distortionless, this is the relation you have to use: L by C, inductance by capacitance ratio equal to resistance to conductance ratio. Now, we can write the characteristic impedance Z0 as square root of L by C. But we know that L by C equal to R by G. So, it can also be written as square root of R by G. Okay. Now, we need to find what is the attenuation constant. Now, what is the equation for attenuation constant? Alpha. Attenuation constant is represented using alpha. Phase constant represented using beta. All these things we have discussed in the transmission line video, formula revision video. So, the attenuation constant can be written as square root of Rg. Now, I am going to substitute the value here for G in terms of this relation. Okay, I'll write this below. So, what is the equation for my attenuation constant? Attenuation constant alpha equal to square root of Rg, right? Now, you can write from this relation square root of G is equal to square root of R by Z0. I'm going to take this relation, connecting these two, Z0 and square root of R by G. From this, you can write square root of G equal to square root of R by Z0. Just substitute this in this equation for attenuation constant, and you will be getting, I'm going to split this square root. I'm going to write it as into square root of G. Now it is easy, right? So put it here into square root of R by Z0. So square root of R into square root of R is R, right? So you can write it equal to R by Z0. This is the relation which we are getting. Okay. That is attenuation constant alpha equal to R by Z0. Now from this question, what all things are given here? In the question, the characteristic impedance is given directly, Z0 equal to 50 ohms. And the resistance is also given, R equal to 0.1 ohm per meter. So, these are the only values we require to find the attenuation constant actually. So, alpha equal to 0.1, that is the value for your R, by 50. The answer coming is 0.002 Np per meter. Okay. Okay, so the answer coming is 0.002 Np per meter. The correct answer or the correct option is option D. So, if you have trouble in remembering these solutions, how you get this equation and all, just study that the equation for your attenuation constant alpha equal to, you can either use this relation square root of Rg, this is one equation which you can use, or you can use alpha equal to R by Z0. These are the two equations for attenuation constant. Now clearly remember that this is for a distortionless transmission line. Okay. So if the line is a distortionless transmission line and if you want to find attenuation constant, you can either use this relation or this relation. Just note it down somewhere so that you don't have to reduce and find the final equation. Okay. Square root of Rg or R by characteristic impedance is at 0. Anyway, the correct answer for this fifth question is option D is the correct answer. Now moving on to the sixth question. The sixth question is from antennas. I've included the question from antennas also along with this. Okay. Sixth question. For a 8 feet, 2.4 meter. So 8 feet is 2.4 meters. So the distance or the antenna height is given 2.4 meter. So for a 8 feet parabolic disc antenna operating at 4 gigahertz frequency, the minimum distance required for far field measurement is closest to dash. Okay, you need to find what is the distance for far field measurement. The equation is far field distance are greater than or equal to 2d square by lambda. Now d is given to you. Lambda we don't know, but you can use a relation lambda equal to c by f. F is given, C we already know. So you can get lambda. So from this we can directly find R, right? So just substitute these equations and find the value for, these values and find the value for the minimum distance required. So first we'll find what is lambda. So lambda is, C is 3 into 10 raised to 8 by F is 4 into 10 raised to 9. It is 4 gigahertz. 4 into 10 raised to 9. So the value getting is lambda equal to 7.5 centimeters is the value for lambda getting. Now you have to convert this to meter. So we'll write it as 7.5 into 10 raised to minus 2. We'll write it afterwards while writing here. Okay. So lambda we have obtained as 7.5 centimeters. Then substitute it here and find what is the R. We'll take R equal to, okay, since we need to find the value, we are going to take R equal to 2 into 2.4, it is in meters, so directly substitute 2.4 square by lambda, so 7.5 into 10 raised to minus 2. Why? Because this is in meters, so this has to be also in meters. All units has to be in same, same. So the value getting is 153 meters, or approximately you can write it as 150 meters is the minimum distance required. Okay, correct answer is option D, 150 meters. Moving on to the seventh question. Seventh question is from Coulomb's law of electrostatics. Seventh question. So mostly all questions, more than 80% of questions are difficult and they are numerical questions. Okay. So the seventh question is, a charge of 2 into 10 raised to 7 Coulomb is acted upon by a force of 0.1 Newton. So the force and the charge value is given. Determine the distance to the other charge of 4.5 into 10 raised to minus 7 Coulomb. Both charges are in vacuum. So the question is very clearly regarding or from the Coulomb's law. Both the charge values are given. The force is also given. You need to find the distance. Okay. The question is given in a little bit twisted way, but anyway it is understandable only. Okay, first we'll write the equation for force. Q1 Q2 by 4 pi epsilon 0 r square. Right. So what is the force? Okay, force is 0.1 Newton. So we'll write in terms of R we need to find, right? So R square equal to Q1 Q2 by 4 pi epsilon 0 F. Substitute the values for Q1 and Q2. Q1 is 2 into 10 raised to 7 Coulomb. Q2 is 4.5 into 10 raised to minus 7 Coulomb by 4 pi epsilon 0 into F. F is 0.1 Newton. Okay. And if you solve this, substitute the value of epsilon 0 and in the electrostatic numericals video I've explained to you that 1 by 4 pi epsilon 0 can be written as 9 into 10 raised to 9 directly. Okay. You don't need to find 1 by 4 pi epsilon 0. It is a tedious task. Just remember that 1 by 4 pi epsilon 0 is 9 into 10 raised to 9. So it is, I'm going to remove it and I'm going to write it 9 into 10 raised to 9. It is very easy, right? So if you solve it, you will be getting the value. You have to find the square root also, okay? The value coming is 0.09 meters. Correct answer is option D. 0.09 meters is the distance to the next charge. Okay, so the answer for your 7th question is option D. Moving on to the 8th question. The 8th question is a theory question. The primary transmission line parameter that is associated with the magnetic flux linkage is dash. AR, BL, C, D, G. So R means resistance, L means inductance, C means capacitance, G means conductance. Okay, so the variables are given. So which is associated with magnetic flux linkage? We all know that magnetic flux linkage is associated with the inductance, right? So correct answer is inductance or L. Option B, L is the element of transmission line, that is the primary element of transmission line associated with the magnetic flux linkage. So 8th question, correct answer is option B. Now the 9th question. Again a theory question. The dominant mode in waveguide is the mode which has dash. A, highest frequency, B, highest wavelength, C, lowest phase constant, D, highest attenuation. So the dominant mode is a mode with lowest frequency or lowest cutoff frequency and highest wavelength. Since frequency and wavelength are in inverse proportionality, if frequency is low, wavelength has to be high. Wavelength, okay. So either of these option is, if available, you have to choose that. Frequency, cutoff frequency will be low, wavelength will be high. So here frequency low is not given. So you have to choose option B, highest wavelength. Okay. So these type of questions, little bit confusing, but you just have to apply your logic. Frequency is low means wavelength is high, or wavelength is low means frequency is high. Likewise, you have to use this relation and then you have to find the answer. Anyway, you should be knowing that the dominant mode is having the lowest cutoff frequency. So correct answer here is option B. The last question, or the 10th question. The condition for a quarter wave transformer is dash. A, Z0 square equal to Z in ZL. B, Z0 equal to Z in ZL. C, ZL square is equal to Z in Z0. D, Z0 equal to Zin. For a quarter wave transformer, the relation is Z0, the characteristic impedance square, is equal to input impedance into load impedance, or Z0 equal to square root of Z in into ZL. So if any of this option is given, it is the relation for the quarter wave transformer. So the quarter wave transformer we use for impedance matching generally. We have discussed about this in the transmission line formula revision video. So the correct answer is option A. Z0 square equal to Z in ZL is the relation for a quarter wave transformer. So these are the questions which I have included in this video. Maximum I have tried to include numerical questions. You can find these type of difficult numerical questions also in especially GATE exams and ISRO exams. Okay, so I really hope that you found the video useful. If yes, please do give it a thumbs up and also share it with your friends. And if you want more videos, please do subscribe to the channel. Thanks for watching and keep on watching.